This decade marks a new era in space exploration. Reusable launch vehicles, ambitious missions, and renewed focus on the Moon and Mars are redefining spaceflight. Designing systems for these complex operations presents significant challenges, often requiring advanced design and simulation tools to accurately capture the physical phenomena involved. One of the most critical challenges in modern spaceflight is in-orbit liquid propellant transfer. Whether enabling multiple engine relights for boost back and landing burns, executing precise deorbit maneuvers for vehicle recovery, or refueling spacecraft for deep space missions, these operations demand exceptional accuracy. Detailed flow modeling is essential to capture transient flow rates and pressure fluctuations required for reliable system design. Every valve movement and every pump startup requires an accurate understanding and modeling of resultant dynamic pressure fluctuations in fuel lines and other equipment, placing stress on lightweight, highly optimized systems. In space applications, mass is limited, safety margins are tight, and failure is not an option. That's why engineers rely on advanced system simulations such as Flownex to predict transient behavior before hardware is ever built. In this example, Flownex is used to simulate an in-orbit ship-to-ship propellant transfer, with a focus on transient pressure behavior within the fuel lines. The basic fuel transfer system is modeled in Flownex, including tanks, pipes, valves, pumps, and control logic. A two-phase tank component is used to model the 𝗥𝗏𝘂𝗀𝗀𝗃 tank, a cylindrical tank with a volume of 103 cubic meters. All of this propellant must be transferred to the ship 𝗏𝗂𝗀𝗃 tank. Initial conditions are set using a steady-state boundary condition. A tank pressure of 600 kilopascals and an average fluid temperature of -190°C is assumed, placing the 𝗏𝗂𝗀𝗃 in a subcooled state. A mass fraction boundary condition defines the fill level, showing that the 𝗥𝗏𝗂𝗀𝗃 tank is nearly full. Initial conditions in the fuel transfer line assume a vacuum and are also defined with a boundary condition. Transient simulations track mass flow rates, tank levels, and internal line pressures in real time. As the transfer begins, a critical event occurs. Opening a valve into an evacuated connector line causes fluid to rush in at high velocity, generating a powerful pressure wave. In this case, pressures spike to more than 10 times the tank pressure, a result that directly impacts component design. These results are essential for engineers. They define pipe strength requirements, valve specifications, and safe operating limits, long before physical testing begins. Rather than accepting these pressure spikes, Flownex enables engineers to test mitigation strategies, such as slowly opening valves or adjusting valve opening sequences. Implementing these mitigation methods in a Flownex simulation of the example problem, the Flownex results show here that the peak pressure is dramatically reduced, from over 7 megapascals to less than 2, while maintaining stable operation. This also reveals an important trade-off. Smoother transients improve safety, but slightly increase transfer time, a balance engineers must evaluate at system level. While this example focuses on in-orbit refueling, the same approach applies to many space systems, from reaction control systems and tank venting to engine startup and ground propellant loading. With Flownex, engineers gain clarity in complex flow systems, uncover risks early, and design with confidence long before launch. To learn how Flownex supports aerospace and high-performance engineering projects, watch our in-depth webinar on YouTube on key technical challenges and solutions, or start a conversation with us today.